Hello everyone, welcome to our session today. I'm so excited to get started. We are diving into data and storage, the heart of system design. In the world of high-scale applications, how you handle your data is often what makes or breaks the system. We'll begin by discussing the scaling bottleneck. You'll find that while adding more CPU is easy, scaling data is where things get really interesting and, frankly, where most systems start to slow down. To solve these bottlenecks, we're going to master 4 essential pillars: indexing, sharding, replication, and consistency. These are the tools that allow us to manage massive amounts of information efficiently. Our ultimate goal today is to understand the evolution from a single database node to a robust, global cluster. It's a big journey, but we'll take it step by step. Before we dive into the technical details, let's think about the apps we use every day. Building on what we just covered about data and storage, let's talk about how we actually find what we need. Think about the apps you use every day. Searching for a friend's profile or a specific post among millions of entries needs to be instantaneous. To understand how databases do this, we use the library analogy. Imagine you walk into a massive library looking for a specific book, but there's no catalog system. You'd have to walk down every single aisle, checking every book spine one by one until you find it. In the database world, we call this a full table scan. As you can see here, this means scanning every row sequentially. It works fine for a tiny shelf of books, but as your library grows into a massive warehouse, performance drops significantly because the work increases with every new record. This is where indexing comes in. Instead of searching the shelves directly, you go to a small cabinet, the index, and look up the book title. It gives you a specific location, like aisle 4, shelf B. By using these direct pointers to data, we achieve rapid query retrieval. We don't waste time looking at irrelevant information. We jump straight to the answer. Next, we're going to peek under the hood to see the actual data structures, like B-trees, that make this magic happen. Now that we understand why we use indexes, let's peel back the curtain and look at the actual machinery. There are 2 heavy hitters in the world of data structures that make this possible: B-trees and hash maps. First, let's talk about B-trees. If you've ever used a relational database like MySQL or PostgreSQL, you've likely used these. They are the most common structure because they are incredibly versatile. A key reason they are the standard is that they are designed specifically for disk-based storage, minimizing the number of times we have to read from the slow hard drive. Plus, they support range queries, like finding all orders placed between Monday and Friday. On the other hand, we have hash indexes. Think of these like a high-speed shortcut. They are built for one thing and one thing only: exact matches. If you need to find a user by their specific ID, this is your best friend. As you can see, they offer O1 search complexity, which is practically instantaneous regardless of how much data you have. However, the trade-off is that they can't help you with ranges. They either know exactly where the key is, or they don't. Take a look at this comparison chart. While B-trees give us O log n performance, which is still very fast, hash maps give us that flat O1 line. We're trading the flexibility of range searches for raw, lightning speed. Understanding this trade-off is the first step toward master-level system design. Building on what we just covered regarding B-trees and hash maps, you might be tempted to index every single column to make every query lightning fast. However, in system design, we must always consider the trade-off. The first major trade-off is the balance between read and write performance. While an index drastically reduces the time it takes to find data, it adds overhead to any operation that changes data. Beyond performance, there's the physical cost. Every index is a separate structure that takes up disk space. If you're not careful, your indexes can eventually consume more storage than the actual data they are pointing to. We specifically call this the write penalty. Every time you insert a new row, the database doesn't just write it once. It has to go and update every single index associated with that table. It's like having to update 5 different catalogs every time a library gets one new book. So, before we move on to how we scale these databases through sharding, let's think about how we decide what's worth indexing. Now that we've seen how indexing helps us find data quickly, we need to address a bigger problem. What happens when our data grows so large, it simply won't fit on one machine? This is where we break the limits with database sharding. In system design, we usually talk about 2 scaling strategies. Vertical scaling is like trying to build a taller and taller skyscraper on the same foundation, adding more RAM or CPU to one server. But there's a physical and financial ceiling to that. Horizontal scaling, on the other hand, is like building a whole neighborhood of smaller houses. It's much more flexible. Sharding is the primary way we achieve this horizontal scaling for databases. It's the process of splitting one giant table into multiple smaller parts, called shards, and distributing them across different servers. To the application, it looks like one big database, but under the hood, it's a team of servers sharing the load. Let's look at this practical example. If you have 100 million users on a single server, that server is going to be under massive strain during peak hours. By sharding that data, we can place 10 million users on each of 10 different servers. Now, each server only handles a fraction of the traffic, making the whole system much more resilient. As you can see in the diagram here, we are effectively partitioning our data space. It's a powerful technique, but it does come with a catch. How do we know which server holds the data for a specific user? We'll dive into those strategies in the next section. Now that we've touched on the why of sharding, let's see how it actually looks in practice with this interactive explorer. On the left, we have a stream of incoming data packets. These represent our users and their unique IDs. Try selecting the range-based strategy first. I want you to watch how those packets are sorted into our 3 server buckets based on their ID values. Observe if the load is balanced. Wait, look at server A. It's basically doing all the heavy lifting while server C is just chilling. It's like a group project where I'm the only one actually typing. Spot on. That's what we call a hotspot. If our data isn't distributed evenly, one server gets overwhelmed while others are underutilized. This often happens in range sharding when certain ID ranges are much more active than others. Now, switch the strategy to hash-based and watch the flow. Notice how the hash function mathematically distributes the incoming IDs to fill those buckets more uniformly regardless of the ID value. As you continue to experiment with different keys, keep an eye on that distribution graph. Finding a key that avoids hotspots is the secret to a truly scalable database architecture. Now that we've touched on the why of sharding, let's see how it actually looks in practice with this interactive explorer. On the left, we have a stream of incoming data packets. These represent our users and their unique IDs. Try selecting the range-based strategy first. I want you to watch how those packets are sorted into our 3 server buckets based on their ID values. Observe if the load is balanced. Wait, look at server A. It's basically doing all the heavy lifting while server C is just chilling. It's like a group project where I'm the only one actually typing. Spot on. That's what we call a hotspot. If our data isn't distributed evenly, one server gets overwhelmed while others are underutilized. This often happens in range sharding when certain ID ranges are much more active than others. Now, switch the strategy to hash-based and watch the flow. Notice how the hash function mathematically distributes the incoming IDs to fill those buckets more uniformly regardless of the ID value. As you continue to experiment with different keys, keep an eye on that distribution graph. Finding a key that avoids hotspots is the secret to a truly scalable database architecture. Building on what we just covered regarding hotspots and distribution, let's look at the actual architectural patterns we use to split our data across multiple servers. First, we have key-based or hash sharding. This uses a mathematical function to assign data to a shard. It's fantastic for ensuring an even, uniform distribution across your cluster. However, it's notoriously difficult to reshard. If you want to add a 4th server to a 3-server cluster, the math changes, and you might have to move almost all your existing data. Next is range-based sharding, which is like sorting an encyclopedia by volume. It's incredibly efficient for range queries like finding all transactions between January and March. But as we discussed on the previous page, this is where you really have to worry about hotspots. If everyone is accessing the current month shard, that server will struggle while the others sit idle. Finally, directory-based sharding uses a lookup service to track where every piece of data lives. It's the most flexible approach because you can move data around freely, but notice the catch. That directory becomes a single point of failure. If the lookup service goes down, the rest of the database is effectively unreachable. Looking at the visual comparison here, you can see there's no silver bullet. Each strategy solves one problem while introducing another. Let's think about which one would be best for a global social media platform. As we just discussed, while sharding allows us to scale horizontally, it isn't a get-out-of-jail-free card. It introduces what engineers often call the sharding tax. Let's break down these hidden costs so you know exactly what you're signing up for. First, we lose the simplicity of joins. In a single database, the engine handles everything, but once your data is split, a query that needs data from 2 different shards becomes a massive coordination problem. You often end up having to pull the data into your application code and perform the join there, which is significantly slower and harder to maintain than a native SQL join. Then there's referential integrity. Most relational databases can't enforce foreign key constraints across different physical servers. If you shard your users and orders separately, the database can't easily stop you from creating an order for a user that doesn't exist. And finally, the resharding nightmare. What happens when your current shards get too full? Moving terabytes of data to a new set of shards while keeping the application online is incredibly complex. It's like trying to move a house while people are still living inside it.